In this collaboration with the University of Oxford and IBM, we were trying to make twofold coordinated carbon, molecules called cyclocarbons. And they could have not been stabilized and studied today. And carbon can have different forms, and then it has completely different properties. So for example, you have diamond, in which every carbon atom is coordinated to 4 neighbors. And then you have graphite, in which every carbon atom is coordinated to only 3 neighbors, with completely different properties. And also in buckyballs, so Buckminster fullerenes, every carbon has 3 neighbors, or in carbon nanotubes, or in graphene. And so far, there's no material of carbon with twofold coordinated carbon atoms, so where each carbon only has 2 neighbors. And this was the goal of the study here, to make such a material and to see what its properties are.
So we were aiming for cyclic carbon atom or molecules that consist of twofold coordinated carbon atoms. And for forming those molecules, we started with this precursor. It has been synthesized in the University of Oxford by Laurel, our collaborator. And the idea was to apply voltage pulses in the microscope to remove those masking groups. The masking groups consist of first a carbon atom and an oxygen, so carbon oxide atoms, and we wanted to remove those to form a cyclic carbon molecule. And by applying voltage pulses in the microscope, we first removed the first 2 carbon oxide molecules to form this intermediate. And we were also able to remove 4 of the CO masking groups to form that intermediate. And eventually, by applying voltage pulses again, we were able to form cyclocarbon consisting of 18 carbon atoms.
Okay, well, after we generated the molecule in a microscope, we can of course also image the molecule. That is what you see here. So it's an atomic force microscopy image of cyclocarbon. Now the question, of course, is what is actually the structure? So because you could have either double bond, double bond, double bond, double bond, so all bond lengths the same, or you could have alternatively triple bond, single bond, triple bond, single bond. Now, in order to find this out, what we can do is we can simulate atomic force microscopy images. So we first calculate the theoretical structure of cyclocarbon using quantum mechanics, and then we can use another code to simulate atomic force microscopy images, how they would look like for the different structures. And based on these atomic force microscopy simulations, we then could clearly determine that the kind of contrast that we saw in the atomic force microscope experimentally, so this 9-fold symmetry, the nonagon, clearly corresponds to the structure of the triple bonds and the single bonds. In particular, we could see from our simulations that the positions of the corners are the positions of the triple bonds, and the edges of the nonagon are the single bonds. So with this way, we could really clearly identify what the actual structure of the molecule is.
So with our approach, we could actually stabilize cyclocarbon for the first time, and also we could characterize it. One more very cool thing about cyclocarbon is that also we can potentially use it to form larger molecular structures. So it's very reactive, and therefore we saw that we could actually fuse it by applying voltage pulses in the microscope with other molecules. And you see here behind me that there we could actually fuse one of the precursors that I showed you before with a cyclocarbon. And we could form a larger molecular structure by covalently fusing those 2 molecules, and that could potentially open the way to create more sophisticated structures in the future to use for electronic devices or so.